So when I look at this thing here, the first thing that we're seeing here is that before the switch is thrown, I got to find what? That initial condition. So the first thing that I got to look at here is that before switch is thrown, I have to determine the IC VC of 0 minus. So remember, always assume steady state. You know, some of you are going to say, well, is it in steady state? And I'm going to say, yes! It's always in steady state when I write that, right? So you got to remember that. It's always in steady state. People say, well, I don't know how to solve that. And I'm going like, what do you mean? This is what I know. I erased the damn thing, right? But you saw what I wrote. I'm making a big deal because there'll be people that are kind of paralyzed and going like, I can't get the IC. And I'm going like, what do you mean? Right? Steady state. Okay? And so now, what happens? I get that steady state. The switch is thrown. So now, after switch, you know, maybe I should just put quotes so I don't have to go back and erase. Right? You'll figure it out, right? My daughter would kick my ass though. She has better English skills than I do, without a doubt. She's only 16. So after the switch is thrown, we do what? We convert RC circuit into a Thevenin. Okay? Then what we do then is that we solve the first order equation. And the way we solve that first order equation, we'll most likely, we'll just use KVL because it's a simple circuit, right? For VC of t. And remember, anytime I write VC of t, I'm talking about that transient period here. And then what I do next here is that I undo the Thevenin circuit. That means back to original circuit and solve the problem. Step one. What am I going to do? I'm going to determine IC. Okay? So here's my circuit now. I look at my circuit, and what does my circuit look like? It looks like this. Right? So I got R1, R2, R3. When I look at that, I got to determine that voltage. Right? So what am I going to use? I'm going to use KVL. If I use KVL, you can see that VC 0 minus is the same as the voltage across the 3, which means it's got to be R3, 1, 2, 3 times V source. I have my initial condition. So now, what do I do next? I throw the switch. After I throw the switch, I convert the circuit into a Thevenin circuit. So then I come over here and I go step 2. I'm going to say switch thrown, convert into Thevenin. So when I throw this switch here, I'm losing R1 now. So what you're seeing here is that my circuit now looks like this. Okay, and I'm after this guy right here now. So what am I going to do? I'm going to remove the load. Okay, so I'm going to determine VTH. So if I determine VTH, I'm going to remove the load. So what I see here, I want this guy right here. So what do? I calculate this using VDR again. So if I use VDR, we can see that VOC is the same as the voltage across the 3. Okay? Just as we would expect here. And now, what I'm going to do here is that I got to go calculate the Thevenin resistance here. So in this case here, this is a fairly nice circuit here. So then if I'm going to determine RTH, well, what am I going to do to that circuit? Well, I remove the load. I'm going to short out the voltage source. So if I short out the voltage source, I get this. And now I'm going to look for RTH right in through here. And you can see that RTH just says that what? 2 and 3 are parallel. So this would be R2, R3, which gives me something like this. So now I have RTH. So I've computed RTH, I completed VOC. So then my circuit now looks like this now. And I put my cap back into my circuit here. And my job now is to go solve this thing. How do I solve this thing? I'm going to use KVL. Right? This is a totally legit thing here. So now, I did step 1, I determined my initial condition. I did step 2, the switch was thrown, I converted it into a Thevenin circuit, right? Because I calculated VOC, I calculated RTH. Yes, sir.
When you converted right under step 2, where you got rid of R1.
Yes.
Are we now just saying that R2 equals R1 plus R2?
No, there's no more R1, it's gone. Right? Because the short closed it and it shorted it out and it killed it. Right?
Okay. Yeah.
Okay. So then, step 3 here is I got to solve the first order differential equation. Let's go do it. So now if I get to step 3 here, I need to determine the first order equation. So when I look at this guy here, I'm going to apply KVL and use the capacitor equation. Right? I'm going to use the capacitor equation. So, in this circuit, we assume here, and rightfully so here, that because they're in series, all of these elements have the same current. So what I'm going to do then, KVL tells me what? KVL tells me that I'm going to have VTH, actually let me write it the other way. I'm going to get the voltage across the Thevenin resistance plus the voltage of the cap must be V Thevenin. But that voltage across the resistor, since we know what the current is, should then be, so now we apply the capacitor equation, which says that IC is C dV dt, and if I just plug that guy in, I'm going to get what? I'm going to get R TH times IC here, right? Should I write this in? Yeah, why not? So then this is going to be RTH dV dt plus VC VTH. Okay, so there's my first order differential equation. What's common practice, we could leave it like this, but the common practice is to divide by this RTH value. So if I do that, you'll see that I'll divide all of these terms out of the picture. So if I look at this guy here, the common thing that we do here is that I'm going to take this, and then I write this as VC dt plus 1 over RTHC VC equals VOC RTHC. This is our differential equation right there. Right? So this is what we call our first order equation in proper form. Why in proper form? Because when we write it this way, I'll be able to use this exact same equation when I get to the inductor. Okay, so just so that we could see that there's sort of like this flawless motion from capacitors to inductors, I want to effectively do the exact same thing. So when I do this thing here, what we find is that it's useful to rewrite this into dummy variables. Okay, the dummy variable that's typically used is that they use x. So what I'm going to do here is that I'm going to use the symbol x is going to be VC. As you probably might have already realized, our time constant tau will take on that form. And then this guy right here, I'm going to define k as this thing right here. And what you're going to find here is that this is effectively our source. K is not a source. It doesn't even have the right units, right? This would be voltage divided by time. But what it does here is that we can't say that that K is the effective source, because it's directly proportional to the voltage. And RC is just a plain constant. So if I was to write this thing here, what we'll see here is that this now takes on the form dx dt plus x over tau equals k. And I would say that it's probably best to look at this equation so that we could transfer this. Now there's lots of ways that you can solve this thing. The easiest way that I see here is just integrate the thing, right? This is essentially just an integral equation, so I can solve this by integration. And I think it's nice to do it by integration because it's an indefinite integral. And as you already know, indefinite integrals have what? An arbitrary constant. But wait a minute. What do we do with that arbitrary constant? We deal with it with the initial condition. It's not arbitrary. It's the initial condition that becomes super, super important in real circuits here. So what we can remember here is that x is a function of time, k is a constant, tau is a constant. So all I'm going to do here is that I just got to isolate the x's on one side and everything else on the other side. And that's what we typically do here. So the first thing that I'll do here is that I can manipulate this guy a little bit. So if I pull this over to this other side, then what I'm going to do here is that I'm going to get a common factor for tau. So I'm going to get dx dt. And then if I move this to the other side, I'm going to pull out a minus sign so that I get x minus tau k divided by tau. Okay? So then I can't really separate the x from, and isolate it, so then I'm going to divide both sides here. So then if I do that, I'm going to get x over x minus tau k must equal minus dt over tau. And this is a real clean indication of why you see 1 over tau in the exponential form right here. So then if I integrate this thing, of course, I'll do a substitution, but note that the substitution here gives me the constant 1, so I don't really care about it. I'm going to get a log, and then to get rid of the log, I take the exponential. I'm sorry, I said log here. I get a log here, I just get a regular t. So if I do this here, I'm going to get the natural log. And so if I integrate these guys, I'm going to get the natural log of what? X minus tau k. And then I'm going to get minus t over tau plus some constant. So if I get this constant here, you can see that my whole goal is to get rid of this guy. So if I want to get rid of this guy here, what I'm going to end up with here is that I'm going to get what? I'm going to take the exponential of both sides here, and I'm going to get minus t over tau, and then I'm going to get e to some constant. Right? Right? I mean, I could, if I take the exponential of both of these, it's the exponential of the product as well. So then if you look at this side here, this guy kills this off, so then I get x, and then you see that tau k, I take it to the other side. So then I'm going to get x of t is going to be tau k plus this new constant here. What should we call this constant? What do I call it? I think I called it a. So then I'm going to get a e to the minus t over tau. Right? So this is the solution that I have right here. So what I need to do here is that now I got to force my conditions. I know what tau is, but I got to force that condition A. And the way I'm going to force this condition so that it's in nice form is that you see that I'm going to do what? Well, I know that the initial steady state has to be this. I know that the final state has to be this guy right there. So I can come over here and I can force this guy to behave this way. So one thing that I can do here is that now I'm going to apply initial conditions. That means x of 0 and then x at infinity here. Right? Those conditions must be met here. So the first one here that I see here is that I could write this at x of 0 minus means that this gives me what? Tau k plus a to e to the 0, which is just 1. And the other thing that I find here is that x at infinity has to be what? That goes to 0, so then I'm going to get a term that's what? Tau k plus a e to the minus infinity, which is of course 0 here, and this guy gives me 1. So what you're seeing here is that I could rewrite my values here. Right? So what you're seeing here is that at x infinity, that guy has to be tau k. So if I plug this guy into here, then that gives me what the a value is. So now I'm going to solve for a. So I got x 0 minus is equal to tau k plus a, but this is also equal to x infinity plus a, which then implies here that a must be x initial minus x infinity. So if I have that, now I can plug that guy right back into that. And, man, can I just write this right here? Because we're done. Let me just write this right here. So that means here that x of t is then x infinity plus x 0 minus x infinity times e to the minus t over tau. So that's our final solution to this differential equation. And unfortunately, we're out of time. Okay? I think when we start to look at these circuits, I think they're way interesting. They got a lot of meat on them, as we would say, right? Or a lot of tofu. Right? Okay, I will see you in lab tomorrow, or